Our next speaker is Professor Prerona Chatterjee. She did her bachelor's honors in mathematics with computer science and physics from St. Xavier's College, Kolkata, and master's in mathematics and computing from IIT Guwahati. She completed her PhD in computer science from the School of Technology and Computer Science at TIFR Mumbai under the guidance of Professor Ramprasad Saptarshi. She was supported by a Google Fellowship in the final year of her PhD. She was a postdoctoral researcher for 2 years, first at the Czech Academy of Sciences, Czech Republic, and then at Tel Aviv University, Israel. Her second year of postdoctoral research was supported by Israeli International Postdoctoral Fellowship. Currently, she is a visiting faculty in the School of Computer Science at NISA Bhubaneswar. Today, she'll talk about the kind of researches going on in the area of theoretical computer science. Let's give her a warm welcome.
So I'm really happy to be here. I was here as a TA 5 years ago, loved it a lot, and I'm really happy to be here again. So what I'll be talking about is basically give some examples of the kind of questions we look at in this area called theoretical computer science. So let's just start off with a puzzle first. So suppose we have like 7 villages, okay, and we want to connect the villages. So currently they are like separated out, there's no roads connecting them, they're segregated, we want to connect them, okay. So we'll just denote a road by some line, and so basically I will say that this village and this village is connected even if there's a road which goes via another village. So it need not be directly connected. I just need that for every pair of villages, there is some road which goes from A to B, can be through some other village as well, C, okay. So is the connection, the question clear? So we want to connect all the villages, and there should always be a possibly indirect road between any 2 villages, okay. And let's assume, just to simplify things, that any direct road costs 10,000 rupees. Okay, just for simplicity. And so now suppose you go to, I don't know, some local government and say that this is what I want to do, and I need some amount of money, okay, and the local government will tell you, okay, you can have 50,000. Can you do what you had set out to do? Can each pair of villages be connected with only 50,000 rupees? If yes, you have to tell me how, and if not, so how many people think yes? It can take some time maybe. So 7, or how many had? 8? 1, 2, 3, 4, 8. 8 villages, okay. I want to connect every pair of village must be connected, and the government has, local government has given you 50,000 rupees. Any direct road costs 10,000 rupees. So this whole language that I've said about each road costing 10,000 and 50,000, what can you simplify it to? What am I essentially asking? 5 roads, exactly. So what I want to say is that there are 7 points, and I want to connect, so every pair should be connected, but only using 5 lines. Is that possible or not? How many people think yes? Okay, let's start off with something simpler. Okay, so there are 8 of them, right? Can you connect them with just 3 lines? Why? For 3 you cannot for sure. Why not? Who said no? You said no. Who said no? Okay, with 3 do you think you can connect? Why? Exactly, very good. Can we connect them with 10 lines? Yes. Okay, what is the number that you definitely think you can connect it with? 7. Huh? Can you prove? Okay, now can we connect it with 5? Yes, how? Can you maybe come up somewhere here? mean, it's just some random 8 points. Hey, no.
They are in a straight line, right?
No. That's cheating. This is 2 different roads. So now what? I mean, can you do with 5 or not? No. So 7 you said you can do, right? Okay, so 70,000 is enough. Do you think it is also necessary? Who said yes? Yes, okay. Why do you think it is necessary? Yes, I mean, good idea, but I mean, you're along the correct thing, but can you formalize that a little? Okay, so I'll help you a little with the kind of language we would like to use. So basically, we have currently, there are like 8 disconnected components, right? And let's say that if we connect 2 of them, so once 2 of them are connected, it's like they are in the same group, so they are connected. Okay? So with this language, can you tell me now, how do you prove that you need 7 lines? You had started off with 8 different disconnected components. Each time you add a line, you are reducing the number of disconnected components by 1. So at the end, what do you want? Exactly. Right? So yes, okay. Every time you connect, it's getting. And at the end, you want 1 component. So what did we say? So the number of components at the beginning, this is general. So suppose is n. At the end, the number of components you want is just 1. And what did we observe? That every time you are connecting, the number of components reduces by at most 1. So like for at most 1, because I mean, you could have done something stupid, like if you have already connected this and then you add another one here, you are not decreasing the number of components. Okay, so that's why the number of steps you need is at least n minus. So what did we do here? What we did is, we had some problem that we wanted to solve. We gave a solution for the problem. That is, we said that, okay, this much amount of resource is enough to solve this problem. But we also gave, so this kind of thing is what are called upper bounds. Okay, you give an upper bound on the amount of resource you need to solve a problem. But then we also gave a lower bound, in the sense that you give a statement of the type that this much amount of resource is also necessary to solve the problem. Okay, so in a very compact way, basically these are the kind of statements we like to prove in this area called theoretical computer science. Okay, so giving the upper bound thing is very natural, right? So you say that you want to solve a problem, you basically find out a solution, right? You say that, okay, this much amount of resource is enough to solve your problem. But then why is proving that something is hard also helpful? One is, of course, to convince someone that no, if this is the problem you want to solve, then you must give me at least this much resource. But there are some other things as well. Like what did we see like today morning, or like whenever you get stuck with a hard problem, whenever we had like these ugly looking formulas, right, which by hand if you try to solve, they are very hard to do. So knowing that something is hard to do leads to other questions that should come to your mind. Firstly, is it necessary to find the exact solution to that problem? Like we wanted to minimize the distance between, we were finding this arb min of what was it called? What deviation? Clustering, yes. So we couldn't get it to exactly 0, right? But we were sort of happy enough that if we could minimize that value, okay? So that sort of thing. So is it always necessary to find an exact solution? What you basically say is that if you can if you know for a fact that the problem that you're trying to solve is hard, then you ask yourself, is it necessary to find the exact solution? Maybe not all the time. Okay, so one classic problem that comes up in this regime is basically called this traveling salesperson problem. Okay, where what you have is again some villages, let's say, and in this setting, so all of them are connected by direct roads. So it's a complete graph on some vertices. And but here the different roads are of different length. Okay, so basically every edge will come with some cost. So every edge comes with some cost. And what you want to do is that the salesperson wants to visit every village exactly once, but also wants to minimize the cost that they occur, that they have to pay for, basically. So suppose they want to travel all of the places, but the length of the roads are different, right? So if they take a longer path, then they will have to pay for more petrol, which they don't want to do. Okay, so is the question clear? So there's a graph, connected graph. Every edge will have different costs. So this salesperson wants to traverse the graph in such a way that they reach every point exactly once, but they also want to minimize the cost occurred. So how do you do this? Now it turns out that this problem in its full generality is actually very hard to solve. Okay, so then what you come up with is so this is again a sub area of theoretical computer science which looks at such problems which you know are hard to solve. What you try to do is try to come up with approximation algorithms. So you try to come up with algorithms which so the kind of questions that they deal with are optimization problems. You want to optimize some function, some value, but solving that problem exactly is hard. So then you say, okay, I don't want the exact solution that I was looking for. What I do want is I want an efficient algorithm. It should be an algorithm that is doable in not too much longer time. I can do it in some 5 minutes or something. And so it guarantees efficiency. So what you want to do is you want to come up with an efficient algorithm, but it need not give the most optimal solution. But again, what you want to do is you want to guarantee some amount of closeness to the optimal solution. So an approximation algorithm will look, so let's look at this TSP example. So so if you know why I've written believe to be hard, is basically we know that this is NP hard. So we believe it to be hard unless something terrible happens. And we know that this can't be solved exactly, but it does have an efficient 1.5 approximation algorithm. What does that mean? That I need not be able to give you the most optimal path that the salesperson should have taken, but I'll give you a path for which the cost is at most 1.5 times the optimal. Okay, so these kind of questions are what are covered under this area called approximation. One more thing that you can think of is that, okay, I may not be able to solve the problem exactly, but am I stating a more general problem than what I had started out, than what I actually want to solve? So does the actual problem that you want to solve have restrictions on the general problem that you are stating, right? So this, of course, can be done in multiple ways. I'm giving you like one example of how you can deal with it. So again, another classical question is that of something called K vertex cover. So again, you start off with a graph, and here it's not a complete graph. So not all pairs of villages are connected, but there are some edges there. And the aim is that you want to place some police stations on this. So you basically want to select some vertices here, such that every road is sorry, I shouldn't have gone there. So every road is definitely under the watch of some police station. Okay, What does it mean? So for you need to select a subset of the vertices in such a way that every edge, at least one of the endpoints, is covered by that vertex, by vertices in that subset. So for this, I already revealed the solution, but I didn't want to. But anyway, so if note that if you have these two vertices is what you selected, then it covers all the edges. So this problem is called the K vertex cover. K vertex, this K comes in because, so this is, so for a 2 vertex cover problem, you would say yes, it is 2 vertex coverable because there are 2 vertices that does the job. It is not 1 vertex coverable because no matter which one vertex you choose, some edge will always be there which is not connected to that vertex. Okay. So yeah, this is the question. For a given K, find out if it is possible to do this by selecting only K vertices in the graph. And if it is doable, then output which vertices will work. Okay. So this set, I mean, these kind of, when you ask this kind of question, what you are basically asking for are something called parameterized algorithms. Okay. So it is a way of dealing with problems where, so this K becomes the parameter. Okay. So suppose you know somehow, like doing some survey or something, you know that this problem is solvable if, sorry, you know that most probably you don't need too many villages on which you need to place police stations. So suppose you know that somehow, okay, then if you know that K is small, then you want to come up with an algorithm so that you can actually output which vertices you need to place the police stations on. Is that clear? So what did we want to do? We wanted to find the vertices where if you put the police station, then all roads are covered. Like all roads are under some police station, right? So for that, it is believed to be hard if both K and N are large. But if K was small, then it is known to have an efficient algorithm. So these kind of questions would come under something called parameterized algorithm. Okay. And then most favorite to me would be the next thing. But before that, again, let's play some puzzle. I mean, let's try to solve some puzzle. So okay, so suppose like 5 of you are a group, okay, and each person think of some 2-digit number, and what you want to do is, as a group, you want to find the sum of the numbers in your group. How would you do it? Just ask each other, no? And then you add them up. But now, let's say you want to find the sum of the numbers selected, but without any of the other group members knowing what you had thought of. So do you understand what you want to do? There are 5 of you. Each of you have thought of some 2-digit number, and you want to find the sum of the numbers thought of by in your group without anyone else knowing your number. How do you do it? Yes, that is one way of doing it. Suppose I don't allow you that. Any ideas? What do you think? Yeah, but no. So you want to find the exact sum. No. I want to find the sum exactly without anyone else knowing. I mean, so as a group, you want to find the sum exactly, but you only know your own number. You don't want to know anyone else. I mean, you don't want anyone else to know your number. No. None of, so for every group member, the group member does not want any other group member to know the number. I'll give you a hint, okay? You have to use some random number somewhere, right? Because otherwise, what do? You have to use randomness somewhere. Suppose, no. Because, I mean, how will you do that? I mean, oh, I see, put it. But that is again similar to something like there is some other node or to which you are sending anything. So in when it should be like there is only conversation, like direct conversation between you, okay? So it's like if you put in something, like people can see that you have put it in. You don't want that. So yeah, the hint is that, yes. Yes, yes. So that's the starting point. Can you tell me what do you do after that? Yeah, I mean somebody else. Sorry, no, not you. Huh? Yeah, yes, Dootika has told the first step. Now tell, like, I want one of the other, yeah. Yes, exactly. Are people convinced that this is secure? Firstly, did everyone understand the algorithm? Huh? So the first person is adding 2, and then each person is just adding their own number to that and returning it to the first person. First person knows what that random number is. So then they can subtract that and just announce the sum. Do you think any one of them would have known anything other than their own number? Because there's, to them, so to every person, it's basically just a random number because of that initial randomness that you had put in. Okay? So that's exactly what you do. And so that's where this comes in, which is like, can you use the limitation? Okay. Are there some questions which need answering? Okay. Huh? Is everyone happy with the protocol? The second, so this protocol will not work if there are only 2 people. In the year. Oh yeah, in the year, yes. So this is only a communication between 2 and 3. So it's not a broadcast. Yeah, so yeah, I mean, so all of these, so everything that you are saying, they are like, basically you will come up with, these are different communication models. The communication model I want is just point to point, okay? Very good, you are coming up with communication models. Yeah, and yeah, so basically the point is that if you know that something is hard, can you use it to do something constructive? Okay, so in the puzzle that we just played, actually there was, I mean, no matter how powerful any of the people in your group were, you couldn't have done anything as such, okay? But let's play another game actually, where we will see where you need limitation of power. So suppose there are 3 of you, and again it's just point to point, so communication has to, and not just point to point but also in a linear fashion. So it has to be that A is talking to B, B is talking to C, and C to, so other direction also, C is to A to B, B to A, but there is no direct communication between A and C. Okay, and A has some secret message that they want to share to C, but not with B. How do you do that? Yes, but but note that, okay, write it in a manner that, very good, yes, but how do you do that actually? So again, let's give some more help. So let's say you have a box. So let's say that A has a box and a lock and key, okay, and C also has a lock and key. Can you now tell me? So can you now say what you mean by, so let's say this is what they have extra, that this person has a box and a lock and key, and C also has a lock and key. Can you use this to actually tell me how you are going to do this? Yeah? No, key, if you give the key to B, then B will open it. No. So they have, so A and C cannot talk to each other. Talk to each other, meaning not even give keys to each other. So there is no communication between A and C. They have just decided on what they are going to do, but there's, once it started, you can't give anything. Everything that happens has to happen through B. No, it's a different lock and key, different lock. But then key, then how does it help? No. Very good. Yes. Did you hear? Can you just say it properly?
First, A will put the paper in the box and lock it with A's lock and give it to C. Then C will put C's lock on the box and give it to A. A will open the lock, one of the locks, and give it to C, and C can open C's lock.
Are you convinced that that works? Is it, yeah, I mean, currently, yes. How can, I mean, I don't know how to do it with one lock. Sorry? No, no, no. This only, I'm just giving them because, yeah. Is the protocol, I'm not following what you're saying. No, sit down only, but say again.
He will be putting,
No, no, A, what is A doing?
he should put his lock
Hmm.
to the,
I mean, on the box or not?
in the box.
Inside?
Yeah.
How is it putting in, okay? As in, but then the box is open only.
Yeah.
Okay, but then the letter is inside the box, so B can see it. Oh, B will. But currently the box is open only, no?
Yeah.
So?
Even though we opens the lock, opens the box,
Huh.
he only able to see the lock, not the message.
Okay, fine. Now, then after that, what happens?
Then he will, the C will be giving his, putting his key and everything, the whole box and all keys and.
No, no. So then C what? Locks the box using their lock and key or what?
He can get another key for it.
No, I'm still not following. So A does not put the letter, just puts the lock inside the box and then gives it to B.
Yeah.
And then B gives it to C. Then?
He can get a key according to the A's.
Oh, no, that's not, that, no. Yeah, so this is exactly what I mean. So here you note that you are using the fact that breaking the lock or coming up, like get what you were suggesting, like getting a key for just from the lock, trying to get a key for the lock without actually having the key. So you are assuming that these are some things that you are not allowed to do. Okay, so that is basically, this is a protocol which is secure if you assume that some things are not doable. In particular, you have to assume that this B does not have the power to either break the lock, like physically break the lock, or find out a key for the lock without actually having the key. Okay, so in the previous protocol, we didn't assume anything about how much power any of you had. But here, it was secure nonetheless, okay? So that is what is called information theoretic security, okay? But here, you have to assume that this B is not all powerful. B, in particular, you have to assume that, okay, so let's quickly go over the protocol that we discussed. This protocol is clear? But this is secure only if you assume that B can either not break the lock physically or does not have the means to get a key for the lock without actually having the key. So this is basically the kind of things you study in cryptography. Okay, so what you do is you want to come up with techniques to have secure communication, but in the presence of some adversarial behavior. Okay. Now, either you come up with, so this, when you don't assume any computational boundedness on the adversary, then that is like something called secure computation, it's one field. But in cryptography, you typically assume that there is, so why do we need that? So for instance, like this, what did we do in the first thing? It was just a simple task of just adding numbers. But in the second task, you are doing something much more complex. It's like you are sending some secret message to one party, sending a secret message to another party without ever having met physically at all. That is a much harder thing to do. Like just adding numbers is easy. So you can imagine that that is something you can do just securely, even if you don't assume any sort of bound on the computational power of the people around you. But actually sending some message from one party to another party without having communication at all through an insecure channel, that is a hard thing to do. So if you want to do this securely, you must assume that this, okay, there are adversaries sitting on the channel seeing what you are sending, but they are not all powerful. So in this case, for instance, they don't have the power to break the lock without having the key. So what we just did is something called the Diffie-Hellman key exchange. So the first time that your computer is talking to a server somewhere else, they do this key exchange in which that secret letter is essentially the key that they are going to use from now on. But before you have a secret key which both parties have agreed upon, you are just talking to some random server. Your computer has not spoken to that server ever before. To talk securely, they need to have decided upon some secret key. How do you do that? What you do is exactly what we just did. They do this to pass communication. And then they finally have a secret key that they then use to talk securely after that. So this was some breakthrough work that was done by Diffie and Hellman. And basically these locks that we had in our puzzle is basically just some function which is easy to compute but hard to invert. For instance, so suppose you are given two numbers, then finding the product of those two numbers is easy to do. But given a number which is very large, which is just made up, is a large number which is a product of two very large prime numbers, coming to get the prime factorization of that large number is hard to do. You can imagine that, right? I mean, some 10-digit number, if it was just a product of two 5-digit prime numbers or whatever, 7-digit prime numbers, then could you get the factorization? Of course, it's not doable. It is doable. But if you try to do it, you will take such a long time that by then these people have spoken to each other, done whatever computation they wanted to do, and closed the channel. So that is that's the boundedness you are assuming, that okay, it's not a problem that cannot be solved. It can be solved, but it is a hard problem to solve. Okay, so that's what basically cryptography is about. So you have adversaries sitting in channels, looking at your communication, but you use some functions which are easy to compute, hard to invert, and something else to then talk securely. So yeah, I mean, so basically I've just tried to give you some examples of sub areas in this area. But again, overall, what is theoretical computer science? You essentially have some problem that you have in mind that you want to solve. You have some mathematical model that describes the abilities or restrictions that you want to work with. And then what you want to do is study the amount of resource you need. Okay, like in the most abstract level, this is what we do in this area. Okay, now these questions can now be again very broadly divided into two different kinds of questions. One is that it's the problem that is more important to you. You want to solve this problem. Okay, so like given a number, you want to find factors. Given a given a graph, you want to find shortest path. You want a chess game, you want to find the next best move in a chess game. This is like some image recognition sort of thing. Like given an image, you want to find out whether it's the image of a cat or a dog. And then you have ChatGPT stuff. You are given a set of string of words. You want to find out what is the word that best fits the next. Okay, so all of these are problems and you want to solve them. Okay, so these are one kind of questions. And then you have the other kind of questions where you are more interested in understanding the model. Okay, so like communication models that you all, okay, so like you have parties which are communicating with each other, so two-party, multi-party. So are there two people who are talking to each other, multiple people who are talking to each other? Is it a compromised channel? Are there adversaries sitting there, or is it a secure channel? Is it a broadcast? So is it like you're just shouting out something to everyone in that group, or are you just talking to the next person? Or so that is point to point. Okay, so there are these different models that are there, different security that you can ask for, And then you ask what are the kind of functions that you can or cannot compute in this model. Then you have actual computers, like general purpose computers, which are in the research world called Turing machines, okay? Then you have quantum computers, you have circuits, you have proof systems, prove or verify games. So these are all different models that are interesting, that have, I mean, they are basically like mathematical abstractions of real world situations, basically, okay? And then you want to understand what are the things you can do in this model, or what are the things you cannot do in this model. If you know that there are things you cannot do, can you use that to then solve other problems? Okay, so these are essentially, very broadly, these are the kind of things, these are the kind of questions that are studied. And what I work in is like a subset, of course. It's something called algebraic complexity theory, where everything that I said, but restricted to algebraic problems. Okay, so from the question side again, like, can you find factors of numbers, polynomials? Can you compute the determinant of a matrix? Can you compute, like, or how hard is it to multiply numbers, polynomials, matrices? Yeah, so it's just laundry list of some problems that you might have. I mean, you understand each of these things, right? But these are actually, I mean, we don't know, we don't have a consensus on what the best algorithm is for these things. So basically, all the commands that you have in MATLAB, right? So currently there are algorithms which MATLAB is running, but most of them we don't actually know that that is the best algorithm there can be. And on the other hand, yeah, I mean, you want to understand the power of some algebraic models, which this is the most well-studied model called algebraic circuits, but there are other things. Okay, and you want to understand this. Okay, and now, yeah. Oh, so what is linear independence? It's like you are given a vectors and you want to find a linear combination which makes it 0. You want ask if it's there or not. So for that is like, instead of vectors you have polynomials. Is there a polynomial in which if you plug in these polynomials, then it becomes 0 or not? So that's something called algebraic independence. Okay, so these are the kind of things. And then yeah, so I mean, it's sort of almost over, but I want to come back to something that I saw you all had done on Saturday, this picture hanging puzzle. Do you all remember this? Yes? Okay, do you remember the solution? Okay, tell me. So let's just fix this notation that going around this is A, going around this is B, and going like this is B inverse, going like this is A inverse. Is this okay? I think it's similar to what you all had done anyway. Now tell me, what is the solution? Yes. So A, B, A inverse, B inverse. And then you complete it. Okay. So this sequence of actions that you've done is something called commutators. Okay, this sequence of action. And this actually comes up in a variety of places. Okay. Firstly, it is a central concept in something called Galois theory, which you will learn in probably at masters. Okay, but this is a sub area of math where this is the central concept. For more fun stuff, it is essentially the sequence of moves that you need to do to solve Rubik's cube. And for more mathematical stuff, this is essentially what you use. So you know that so degree 5 equations, you don't have a closed formula. To prove that, you can actually prove that. And again, commutators come up in the proof and some other stuff. And also it comes up in algebraic complexity theory. So you don't have to understand what that means, but it basically comes up in the field that I work in as well. And if you want to find out more about commutators, then look at this video. Okay, it's a fun video where you learn how to like actually understand how you are solving Rubik's cube. Yeah, I think that's about it. Okay, I've taken pictures, whatever. Okay. And now three, I mean, I know again that you all had been told to think about three things, I mean, three nails. Did you think about it? What? So what was the 2 solution? 2 ka solution was A, B, A inverse, B inverse. What do you think you will do for 3? Don't have to tell me exactly what, I mean, so again, it's of course A, B, C. Just tell me how you will get it. It's of course going to be a long formula, but just tell me how you plan to solve. Yeah, but yeah, that is true. So, I mean, so basically what I want to say is that you don't have to do too much more. So you already know the solution for 2, right? How are you going to use this solution to solve 3? What are we actually done here? What was the idea? What was the idea behind this? The idea is that A inverse is identity, right? So basically if you remove anything in the middle, it should not be there. If you, it's like if you remove this, then it just becomes identity and it falls. If you remove this, this becomes identity and it falls. But because of these things in the middle, it's not falling. That's the whole idea, right? So how, now for 3, how do you extend this solution to give a solution for 3 nails? Exactly, exactly. So you take, so let's just say you take this whole thing to be A, or let's say A. And then you do the same thing. So you do A, C, A inverse, C inverse. And now plug in this A, or whichever, I mean, you know, that's, does that make sense? So it's just going to look like, so I have put this B.Sc whole thing as one group, and so all you need to remember is that when you're doing the inverse, the order also reverses. So C, B, C inverse, B inverse ka inverse will be B, C, B inverse, C inverse in the other direction. Okay. Yeah, so that's it. Last thing is I just want to advertise our department. It's a very small department. It's I mean, it's currently very small. We are growing, but we already work in some of the things that I spoke about. So the secure multi-party computation was basically this thing where you are trying to add up numbers without knowing. Machine learning data clustering is basically, we already saw machine learning, everyone knows. And algorithm and complexity is again stuff that I spoke about. Okay, so these are already some things that we are already doing. And we are, of course, looking for motivated PhD research people who want to do research in this area. So if you are interested, please contact me or visit the webpage. And yeah, any questions or stuff.
Are there any questions? If not, let's thank the speaker. Thank you, ma'am, for the informative talk.